So 5. So on the same axes, sketch the graph of y equals x plus 2 and y equals x squared minus x minus 6. So it looks like you've got a linear term and a quadratic term. So that's why I put some steps over here. Showing the coordinates of all the points at which each graph crosses the coordinate axes. So we're not really concerned about when it hits. That's why I did this infinite dotted lines. You will in the next part though. So to sketch this carefully, my tip is to break it down into first the quadratic bit and then the linear bit. For the quadratic bit, it's always important to find out where it hits the axis, and to do so, you have to factorize the quadratic expression. So to factorize it, all we need to do is figure out two numbers that multiply to make this 6. And that is, of course, 1 and 6 or 3 and 2. And then using the same two numbers, we got plus and minus them to get a negative 1. Imagine this 1x minus x is minus 1x. And of course, 3 and 2 has a sum or difference of 1 or minus 1. And to get the same expression, it has to be minus 3 plus 2 will give us minus 1. So that's easy. And in doing this, you can clearly say that if it's x minus 3, then it must hit the x-axis at 3. And x plus 2 must hit x-axis at minus 2. So literally just flip the signs. Okay, and because we know it's quadratic, it's a U shape because it's positive. So just draw a U shape, cut out minus 2, and then cut that one at 3. And you know that it's going to hit at minus 6 on the y because we know that the y-intercept is over here, it's minus 6. Another way to figure this out is literally just plug in x equals 0, because remember, it's on the y-axis. And if you're on the y-axis, x is 0. So if x was 0, y is minus 6. So that's done. The linear one's even easier. You literally just plug in where it hits the axis. So what I did here is I plugged in 0 for x and I got 2. So our first coordinate is 0, 2, which is up here. And the second one is when I figure out where it hits when y is 0. That is x equals minus 2, which is over here. And then you just connect the line. So, and really, in reality, it's probably better if I drew this curve a bit, more dented inwards. So the line can actually hit this other side of the curve, because it will hit eventually. But yeah, let's look at B now and C. So on your sketch, show by shading the region R defined by these two inequalities. All right, so it looks like we got the same equations from part A. So we had this one and this quadratic, but now it's a less than and a greater version of the linear and quadratic. Now what you want to do here is firstly, let's work with the linear term. My tip is to use the previous graph, so I copied it right here by the way guys, and I kind of dented it inwards to show that it hits. And all we want to do is literally do this condition. Draw the straight line across here and test values on each of these planes and see where it's true. So I've decided, okay, let's test 0, 0, because we know it's below this blue line and it's on this quadrant, it's on this side, on the bottom side. And when you plug in 0, 0, we find out that you get 0 is less than 2. And this is a true statement. And because it's true, this means that the inequality is actually going to be on this side. If I plugged in any values above over here, for example, let's pick something above. Like let's say, I'm going to probably write this down. Let me just get my pen out. Red. Suppose we chose a coordinate up here. So we could say that would be, let's say 5. So let's say that was 0, 5. If you plug into this equation, you're going to get 5 is less than 0 plus 2, which is 5 is less than 2. And this is clearly false. So this means this is wrong. So this side, so any coordinate you place on the above side is false. So that's why I put these X's, indicating that this side is completely false. Now let's look at the quadratic side, yeah? So I've done quite a bit over here. Using the quadratic term, this time you've got a few more things to do. I decided to work within the inside and the outside. So one thing to note, when you work within the curve, it will be the same answer. If you work in the outer part of the curve, it will always be the same as well. So for instance, I decided to try 0, 0 because it's in between the curve. And plugging 0, 0 into this quadratic equation, I did it over here. Turns out you get 0 is bigger than minus 6, with x is 0 and y is 0. And that is true. Because it's true, that means this is going to be the true reading. And therefore, the outside must be false. You can test it as well. I tested it to show you guys. We plug in other coordinates, you get false. So then you just put x's on around it and make sure you shade in the middle and call it R. And that's it. Okay, part C. Now, hence or otherwise, find the set of values of x for which this equation is less than 0. Now, take a note. This equation here is not the same as these two. If anything, you can kind of see that it looks like the quadratic equation, but it's gone down by 2, and x value is gone down by 1. So actually it's x plus 2 into this one. This is a simultaneous equation. What happened here is that they used a quadratic equation and equated it to the linear equation. And then they subtracted x across and 2 across to get the same expression. And I'm guessing they did it in this format. Yeah, so that's what they did here. Now, the easiest way to do this is to factorize this equation or find the critical values. And just to look at this graph, you can kind of see where the set of values where x is. It's talking about the range from here up to where it goes up to. But because we're looking at this point, we're trying to find up to here, what this coordinate is. Once you find that, you can find the exact range. So when you factorize this one, turns out you can get x is minus 4 or plus 2. So you get x equals 4, x equals negative 2, which makes sense because this is x equals minus 2 and x equals 4 is here. Then all you do is literally realize that it's within. And because it's within, it has to be the within interval.